All right, last video for this lecture. We're going to talk about dynamics of circular motion. This is something that we have brought up before, and if you remember, we had two equations. I basically just described to you what centripetal acceleration is and gave you two equations that could make your life easier. And so I'll write these up again. We called it radial acceleration. And so that was v squared over r. That was one of them. A little bigger here. And the other one was a rad. It's also equal to 4 pi squared r over t squared, I believe. Yes, over t squared. So there are two equations. We introduced them before. Make your life easier, right? So after this video, there's a demo video that I'm going to post that might give you some more physical intuition into centripetal acceleration. But I'll point out now, try to avoid using the word centrifugal force or centrifugal things. This is just a misconception. It's a misunderstanding of Newton's first law. So if something is traveling in a curved path, like say you have a weight on the end of a string and you're swinging it around, it's tempting to say that there's some outwards force, right? The way that it wants to go, like it's pulling against you, and so there must be some force on the object that's going that way. But it's not that at all. It's if you let go, say here, if you're swinging it around and you let go here, and there's no more forces being subjected to it, it would just continue tangentially along that straight path, tangent to the curve. The only reason it's curving at all is because you're providing a force inwards, the tension on the string. You're providing that radial acceleration. If you were not providing that, then Newton's first law applies. There's no net force on it, and so it's going to continue at the same speed and the same direction as it is currently going, right? So if you've stopped your net force on it, then it just keeps going in a straight line. So there's no centrifugal force. There's a centripetal force, rather. It's counterintuitive, but hopefully the demo will give you a better sense of and prove this to your mind. But I want to go over one quick example that might use these, since we've now unlocked a few new tools. And that is this example here. No, not that guy, this guy. So this is kind of a weird one, and without talking about this explicitly, you might be a little lost. So I feel like I had an obligation to cover it. So, an inventor designs a pendulum clock using a bob with a mass m at the end of a thin wire of length L. And they give you a picture here I'm going to bring over. This is the picture. Make sure you can see all that. Yeah. So instead of swinging it back and forth, the bob is to move in a horizontal circle with constant speed v, and the wire making a fixed angle beta with the vertical direction. So this is the situation. The ball is going around here like this, and it's on a string of length L, and that angle that spells out this cone, I guess, is beta. So it's called a conical pendulum because the suspending wire traces out a cone. So find the tension F in the wire and the period T, the time for one revolution of the bob. So find the tension, that's pretty familiar, but the period T for one revolution and the fact that it's going around in a circle, this isn't linear motion like we've been dealing with. You have to introduce these new tools here. But we'll approach it the same way. So one, what are we looking for? We're looking for the tension T, and we're looking for the period. And so therefore, I shouldn't use capital T for the tension. I'll say F sub T for the tension force, and the period, right? Capital T for period. So draw a quick sketch. I'll just reference this one here. This seems fine for me. So this has some mass m, right? And we know that there's a radial acceleration here, a rad. In order for it to be going around in the circle. Right? Otherwise, it would be just continuing on in a straight line. They tell you that this is r, and they say it's at constant speed, which is important. So 3, so that was step 2, right? Step 3, we're going to do a free body diagram. So free body diagram of this weight. So it has some mass that's not negligible, so it has some, I'll do it a little bigger, has some weight, mg, and it has this tension force this way, force tension, you have to label it that way for this problem, and that's about it, right? That's about it, but let's choose our axes. So I've done it again. Positive y-axis is going to be stuffed up here. Positive x-axis, we'll say this way. Yeah, actually, since the acceleration is that way, let's do it in the direction of the acceleration instead of inverse the direction of acceleration. So let's do this, and I'll try to keep track of that explicitly and not have a mistake occur. So now, let's find the components. So let's go back to a color. Components here and here of the tension force, yeah? So there's some components going on here. What is our angle? So this this angle here is beta. You know, convince yourself that that's true, right? Because this is straight up and down, and this is the same angle as this rope or the cord. So if that's beta, then this here, this must be ft sine beta, and this must be ft cosine beta. Right? So that's step 3 done. Step 4 is to get our equations, and we're going to do that in the same way. So step 4, sum of the forces in the x direction. So in the x direction we have this component force, and it's in the positive x direction, double checking myself. So ft sine beta, and there is some acceleration, right? So that's why we did that. So ma, and that's a rad, it's the radial acceleration, just to remind ourselves that that is the type of acceleration we're talking about. I will label it there. All right, and then the sum of the forces in the y. Fy is equal to, we got 2 going on. We have, so the y direction positive is up, we have it, so ft cosine beta minus mg, and it's not moving up or down at all, so there's no acceleration in the y. So there's our equations, but we probably need another one involving the period, right? Since we're trying to solve for the period, we probably need one more equation involving the period, and that's going to be our radial acceleration equation. So I'm going to write that over to the side here. A rad, just copying it from above, 4 pi squared r over t squared. There it is. So those should be our 3 equations that get us everything we need. We want to solve for ft, and we want to solve for the period. So first, so we'll go for gold now. Ft is pretty easy. We can do it just with this equation alone. Ft is equal to mg over cosine beta. And that is one of our answers. Done already. That was the easy part. Now, we involve our period. We need our period. So we have this expression for radial acceleration. We have this expression with radial acceleration. And so we can plug one into the other, right? So I'll plug this guy into there. And we'll do ft, which we have an expression for, but I'll fill it in a sec, times sine of beta is equal to m times 4 pi squared r over t squared over t squared. Really, it's this that we want, right? So we have this expression. So we have mg sine beta over cosine beta. I would turn that into tangent, but I'm not sure if we might need to do other things along the way. So we'll leave that for a quick second. And then we're solving for, so this is equal to m4 pi squared r period squared. We're solving for that period, so I'm going to bring the period over to the left side. T squared is equal to, I'm going to bring everything else over on the right side. M4, well, we have the m's that cancel out here, right? M's cancel. Anything else cancel? No. Okay. So we have 4 pi squared r times cosine of beta divided by g sine beta. And then this is left over on that side. And that should be where we're at. Yep, well, it confirms with my notes. And so then we just take the square root of the whole thing. So that would be 2 pi, comes right out of the square root. R over g, but this, let's see. Yeah, so this would be tangent on the bottom here. Tangent beta on the bottom. So r over g tangent beta. But r is the radius, and we can go a quick step further here. So if you look here, r, we can express r in terms of L if we want to. R is equal to L sine beta, right? L is the hypotenuse. So L sine beta. And so we could go one step further, and we should, to get 2 pi square root of L cosine beta over G. And that's the whole thing there. All right, so those are how, that's an example of how the radial acceleration equations come into play to help you out when the acceleration isn't linear and it's in a constant circular motion. Then you can use those equations. Okay, so one last thing. I will post a PDF of the section, but there's a really nicely written section on the fundamental forces of nature. So we've kind of introduced all these different forces: tension force, friction force, and you might just be wondering, is the rest of physics just cataloging all these different forces, and the rest of this class is going to be kind of boring? Or how does what we're learning fit into the large picture of physics? And so it kind of goes it's like 2 or 3 paragraphs, and it just gives you a nice roadmap. If this is all of physics, right, that we know, and what we don't know is also maybe represented by a question mark that we know we don't know, then it just tells you, okay, we're here, and this is what we're doing here, and this is the rest of it. It's nicely written, and I think it's a good thing to introduce, but I don't want to just stand here and read it to you or paraphrase it. So I'm going to post it available for you, and so that it's available for you, and you can just read it on your own. And that ends this lecture. See you next lecture.